First, to solve mathematical problems, we need to have a mathematical view of a chapter. And for mathematical view, only a few lines are necessary. Okay. For example, general equilibrium as a topic, it has three distinct parts. Number one is consumption, and number two is production. These two are separate. And there is a third thing which connects these two. Two entities which connect them. First one is price ratio, and the other thing is labor. Okay, not labor really, labor and capital, or possibly resources. Okay, so labor and capital and resources in general, and px by py. These are the two things that connects them. Problems on Walras law are easy, but problems on these connection, they are not. Anyways, so in consumption, I have MRS of the ith guy, MRS of the ith guy equal to px by py. So that's one rule. In production, I have MRT equal to px by py. That is another rule. But with variation in production functions, other than these two, all the rules must be remembered in a very general fashion. Okay, so that because of that, the descriptive definition of what a GE is very important. For example, where I've given a problem, I'm looking for some of the things. Number one is I'm looking for a scope of utility maximization. So there is a scope. It may not be required always. Okay, there is a scope. Number two, I'm looking for a scope of production maximization. And also I'm looking for some connections between these two. Okay. Now, one of the easy way to connect them is PPF. Okay. Now, construction of PPF in general, we feel that constructing PPF is very simple. It's not. The target of PPF is, as I said, so mathematically speaking, the target is going from an L comma K plane to X comma Y plane. So that's what our objective is. And that's our job. Now, so what I'm saying is I had a function which involves L and K, or I had a lot of functions which had L and K. Okay. And then I'm moving to some function which had g of x comma y. So many of you constructed a PPF which involved both x, y, I mean all of x, y, L and K. It's hard to conceive where is the parameter, because if you write something which is in which looks like this, then all are variables. So how can I possibly draw it on a plane, on a 2D? Okay, it can be done. So when I'm looking for PPF, I'm moving from here to here, and apart from XY, there can only be parameters. Okay, so that's the first thing. The second thing about PPF, mathematically speaking, is that it's a frontier. So frontier means highest scope. Okay, so more than this, more than the point that is on the PPF, it's impossible to produce. So you have to find that. It's not always that easy. Okay, and for multiple inputs, the job is very different from what one thinks. Okay. Okay. One of the ground rule is this: if I have two PPF which looks like this, then I always take the, let's say this one, which is at the which stays below. Okay, I don't take this one. No, I take this one. All right. Okay, so that is one rule. Now there are the problem is that to how to know that I have whatever I have done with a problem is correct. Because in welfare there is always this act of second guessing. So by which I mean you can equate price ratio with MRS, you can equate price ratio with uh, MRT, and doing two of them may produce different results. Okay, and to that extent you have to be very you, know, you have to be very you have to understand which one to take. So I need some boundary conditions. Now, Pareto efficiency from a mathematical point, from a problem solving point of view, Pareto efficiency is essentially, it talks about some form of a boundary condition. So it gives us something that will always happen. What are they? So for example, resources will always be exhausted. So we will be on PPF exhausting resources. Okay, and unless in a very okay, let's not write even that, unless in very special cases also not true. Okay, so first of all we'll be on PPF exhausting resources. So for example, if you're solving for 13.2, you must look for exhausting the complete labor, or you must at least at the very first scene you will know that all labors will be exhausted. So that's a boundary condition. Unless that happens in the end, okay, you can't guarantee whatever you have done is right. Okay, so the theory provides some cross checks which tells us that whether your solution is correct or not. So this is the first one. The second one is this idea that total uh, the simple idea of total supply equals total demand. Okay, so in case of problems related to general equilibrium, there are three things, as I said, three components. So one component deals with consumption exchange, yes. Now it will be a complete problem of consumption exchange, and if it comes with endowments. Okay, so a complete problem of only consumption exchange, it comes with endowments. If you look at the solved problem I have given, you will see that. Number two is of production. Now, regarding production, I need to know the first of all, there is an activity of profit maximization. Okay, not always it is. It's not always that it is required, but in some cases it is required. In production, you have to look for how the functions are. So, for example, if I have some functions where x equal to 2l, the job is pretty simple actually. It's l equal to x by 2. But if I have x equal to what is the other one? K 0.5, L 0.5, and y equal to K 0.5, L 0.5. Then what I have to think is that whatever I end up with, it has to ensure some sort of optimum. So whatever I do, I have to travel through a optimum point. Okay, and that leads to profit maximization. Because otherwise, if you separate them, the separation is not actually easy. Okay, the separation is not possible actually. Okay, all right, and you have to separate it in a sense that now the original intention is okay. If this is true, then probably PPF will be x equal to y. So that's nonsense. Okay, all right. So these are the two things. Whenever resources are given, as I said, resource connect these two and gives us a complete problem of general equilibrium where we are asked to solve everything. Now, one of the complex and complete setup, I've, the solution that I've given you is one of the complex and complete setup of GE where you have um, inputs, I mean production functions where they are in multiple. I mean they're not separable in that sense. Okay, so where you can't do things like this. Then you have consumption, which is related to the uh, use of resources in production, and then there is wage, which have some values. So the first problem 13.2 it tells you that assume W equal to 1. So that simplifies the job actually. Okay. All right. So when I'm looking at this, resource gives us income, and consumption gives us the way to spend, and how much to spend depends on is limited by how much to produce in the production. So at times it may feel that I am talking in circular. So it's a kind of circle, but the boundary condition is very important, and it is the fact that everything has to be exhausted. And to start with, labor has to be exhausted. Okay. All right. So with this background, we will start. Okay. So first, I'll talk about 13.2. Many of you actually solved it to a large extent, but couldn't complete it. And there can be reasons for that. Okay, so first of all, for a big problem like this, we need to segregate the information. So that's the first step. So what are the information? So there are two goods, X and Y, and then we have two production functions here. Let me just see. Okay, so if I start reading the problem, then the first things that I come with are this Smith guy has a labor of 10, Jones has a labor of 10. Okay, so there are two individuals, then X and Y, ice cream and chicken soup. Okay, then there are utility functions which are Cobb-Douglas, homogeneous of degree 1. So these are something that you have to understand just by reading things. Okay, you are not supposed to. Some of you actually had written in English why those excess demand functions are homogeneous in prices. I'm not asking a question of English literature. Next time you do that, you use function to prove mathematically, to show mathematically why they are homogeneous of degree 0. Okay, the idea is not to ask you what we mean by homogeneous of degree 0. The idea of was that you will be showing by calculation that they are homogeneous of degree 0. Okay, so that's not the kind of smartness we are searching for. Anyways, so this one MRS is, so that's simple. I'm not going to calculate all of this, so they'll be just 3 by 7 y by x. So many of you That's pretty easy. That's easy because these are tasks of first sem. Okay, now first of all, uh, one rule that whenever you look at this, one rule that suddenly comes up in your mind is that, okay, so these are two MRS, and I know in equilibrium these MRS will be equal to px by py. Now, if you do that, then you'll find that you are actually writing this, right? Which gives you something like this, which is completely meaningless. So you identify that equalizing something with px by py, that something is not this. Okay, it's not this. So one option is gone. So simply there is one other option. What is that option? That is option is MRT. So immediately realize that, okay, so if I have to find this, my first job is to find PPF because MRT comes from PPF. So that's how you identify what your job is, because in a problem coming from a specific chapter, theory gives us very limited option of operations. Okay, so if you feel confused, then you do every operation that comes in your mind in relation to what you have been asked to answer. Okay, so you try everything. Okay, that's called trying. It takes time. Yeah. Anyways, because generally what happens is uh, you know your the way the general structure of education always asks you to search for methods, right? So okay, every time I see px by py, it will be equated to MRT. There is nothing like that. Okay, it changes from problem to problem. But the point of learning is that there are only two scopes, this one and this one. So here this is not working, so this one. Okay. All right. So the rest is pretty easy, right? So x equal to, so now we'll go to production functions. Now it has been said that these two guys, they're indifferent between producing x and y. Now why such a line is even written? Because generally we assume that kind of things. The reason is that if it was otherwise, then combining production would have been a problem. Okay, so it is because of this indifference that it is given that they are indifferent. One result that we find at the end of this problem, it holds because of that English sentence. Okay, so we'll come to that, but just understand this, that sentence, it has mathematical importance. Okay, all right, so x equal to L. So let me write Lx. Okay, it helps. So 3Ly. All right. So then you know all of this, right? Yeah, that's quite simple, right? So Ly will be y by 3, and then you sum it up, and then you look for resources. So what are the resources? The resources are 10 from this guy, 10 from that guy, right? So this. Okay. Now, how does that come? Because you see, the point is that the original equation is Ls plus Lj equal to 20. Right? Now, since they are indifferent, I can write that this sum and this sum, they are same. Note this. I'm not writing Ls is equal to Lx or Lj is equal to Ly. This is something that I'm not writing. What I'm writing is that these two are equal. And what I said, one of the boundary condition is that this equality must hold. Okay, so that gives me that x by 2 y by 3 plus y by 3 is equal to 20. So this is my PPF, and then it's pretty easy, right? So then you differentiate and you find MRT, and the moment you find MRT, you have px by py. Okay, so basically you just find the slope. Okay, so what is the price ratio? It will be, I think, 3 by 2, right? Okay, simple divide dx and that sort of thing. Now, once you have that, the rest, the next problem. So this is my answer of the question A. So this is the answer of question A. Now once you have A, the answer of B is a second semester level problem. There is nothing. So you have got PX by PY, you have got MRS. What you have to find is what are their demands, and also you know this thing. Okay. So let me erase this part. Okay. Now one thing that is true, that you see in first order conditions that we have done in the utility maximization problem, we had three conditions. Number one is basically this number one is about x differentiation, number two is about y, and then there is about lambda, which basically gives me budget constant, right? Budget constant. Okay. Now so I have px by py, and so it's very easy to construct the budget constant. Now here, when I'm constructing it, okay, so I know basically, right? I have I know now the role of that sentence comes in. So let's say anybody, Smith, let's say, so he can produce, he can go for x by 2 or for y by 3 because he is indifferent in production. So I have to add them, and his resources are 10. Okay. Right. Now, if you have to have a now, if you want to convert it in a okay, I can do it this in real terms, but if you now if you want to convert, you can write this 3x plus 2y equal to 60, and you will see that our px by py, that actually appears kind of here, right? 3 and 2. Okay, you can visualize, directly see them basically. Now, so that gives you the fact that okay, I'm doing the right thing. I mean, the construction of budget constant is correct. Now here comes the role of W, wedge. So had the wedge been anything apart from 1, I would have had it here. So it is basically 60W. Okay, that's the earning. Now since it is given that you treat W as 1, you don't have them. Because you have multiplied 1. Okay, so that's the idea, and rest of it is a second semester level problem, right? You find the optimum x star for Smith and y stars for Smith and then Jones and everything. Yeah. Okay, that's very easy. So what are the amounts? So the amounts, if you solve them, they become, okay, let me see. So that's 3/7 by x. That is, what are they? Yes. So for Smith, they become, let me erase this. For Smith, it's 6, then it's 21. For Jones, this is, what is this? This is 10. And this is 15. Okay, so now what is the total amount of x that is needed? That's 16. And y, that is 36. Now I am going to labors. So for x, the required labor will be 8. And for y, the required labor will be 12. Okay, divided by 2 and divided by 3. So that gives me, it sums up to 20. Now in the answer, you have basically two choices. Okay, you can say that Smith is going to give the entire labor for x, and then the rest of 2 for y, and Jones will go entirely to 10, sorry, to produce y, or the otherwise. Okay, so there are two options, and both of them are correct as an answer. So let's see. First of all, that these guys, they've exhausted their natural resources, so that's one of the boundary conditions that is satisfied. So I'm working with an economy which is producing the maximum that it can produce. Okay, so that's another that says that okay, it's we are working on the Pareto line. Now the problem, the solution is about the fact that how this labor will be divided between x and y, how much amount of x and y will be produced, and they have to cope with the price ratio. Okay, so that the problem is about that. But something that will always happen is this: the labor resources, they had to be exhausted, and the exhausted resources, they had to they have to go the full way. Okay, and also obviously if 16 and 36 are the total production, then they have to match these. So when I'm coming from their demand to this line, I'm using one of the boundary condition, the second one, that demand must equal supply. And when from this I'm coming this to this, I'm using production function, but I'm looking for the answer, because this answer ensures that I've done correct. Because if I was wrong, then the summing of these two labors, they would have not been equal to 20. Okay, so that's the indication. Okay, so welfare problems are big, huge, and that's fine. What you have to remember is the mathematical view that I said. There is there are some conditions which tells us whether I'm solving it rightly or wrong, and there are some parts where I'm asked to solve maximization problem, either of utility or of profit. And the first one that I've done, so there are two things which are quite difficult actually. So the first one is to find price ratio. So as I said, there are two options: one is MRS, one is MRT. If you if you see that MRS is meaningless, you learn that okay, I have to go for MRT. Okay, so that is the first one, and the other one is PPF. So finding PPF can be quite problematic. So that's why I have solved two different problems and sent to you. Okay, number one, the first one is pretty simple. The second one is complex. So I've seen also that you have quite, I've seen them, because you have solved the easier PPFs, and for the difficult ones, you couldn't solve them. But you can look for the complete problem that I've seen. Okay, there is a solution of solving PPF also. So in the next session, we'll just join, and after say 10 minutes, and look into the fact that we'll look into how to construct PPFs. Okay, in a problem like 13.3, the answer of which you have, some of you have given very interesting answers. Like D says that C, the PPF in C is concave, so I've written a concave. That's good. That looks good, you know. But concave doesn't mean the function has to be smooth. Okay, so that doesn't carry any meaning. All right. But one of the good thing is that yeah, all of you actually successfully solved the problem on Walrasian and excess demand. It was a simple equation, right? Sum of RPI EDI equal to 0. But yet you have solved them and correctly solved them. So that's pretty good. The law was the idea was, yes, the idea was to directly apply this rule, right? Sum of our PI EDI equal to 0. I runs from 1 to 3. So that's good. So you can consider the fact that okay, you can do problems on excess demand functions. All right. Apart from that, 13.13, we are not going to approach that problem today, because we don't we didn't have we won't have time. Other than that, even in 13.6, you have solved the PPF quite beautifully, because in 13.6 also there are problems which are only labor. Okay, and so it was pretty easy, x square, y square, and all of that. So solving that was kind of easy. Okay, so and then you have solved But I think that you had quite a problem solving C, problem C, 13.6, question C. So yes, you have successfully solved 13.11. You have successfully solved 13.6 A and B, and then initial parts of 13.2. Okay, so that you have done. So that's okay. I mean, so you can understand, how far you are from. So I've given you 1, 2, 3, 4, 5, 6, 7. So I've given you 7 problems and you have solved. So walrus law was very easy. So there was okay. So I'll say 6, and out of 6 you have done. Okay, some of you actually solved 13.5 also, and that was good. Okay, so you understand consumption exchange. I'll give you that, and you understand consumption exchange. Okay, and you can solve simple PPFs also. But what you dangerously lack is actually solving for PPFs which are quite difficult. So we are going to learn that in the next session, how to draw PPF, okay, how to think about finding PPF. It's easy, it's not difficult. Okay. So apart from that, rest is fine.